presentation on a low-cost vibrometer. John, we have Jake, Erik, Robert, and John Lee. And our project was to design a vibration measurement device with real-world application to measure vibrations in things such as heavy machinery, vehicle engines, and CNC machines. Our presentation will be focused around the vehicle application. We made it so that any user can use this and for day-to-day purchases such as an automobile. So what happens is a person can take this unit, place it on the vehicle, and understand the overall performance on the vehicle they're thinking about purchasing. We also made it so it would be cheap, portable, generic, and off the shelf, so it can also be used in measuring vibrations and such things as for the maintenance on the heavy machinery. For heavy machinery, so that you can be able to do the maintenance and save money on the maintenance, as well as the overall well-being of the user, to prevent illnesses such as white fingers, which is caused by exposure to excessive vibrations and causes damage in the nerves of the fingers. We also designed it for users who have no idea what a vibrometer is, as well as advanced users. We made it cheaper than products on the market right now. A non-laser based unit is around $500, and a laser based unit would be around $2,000. Our goal was to make ours under $100. We also wanted to make it so that you'd be able to use it on a wide variety of electromechanical systems, as well as use a graphical user interface that have detailed information, easy to understand.
Now, this is just an architectural view of our system, everything from the sensors to the PC unit. Two major sensors that we use for an accelerometer and a microphone, which are both interfaced with a 16-bit microcontroller with microchip. The 10-bit ADC within the microcontroller samples analog inputs from the sensors and transfers the data approximately every 200 milliseconds via a Bluetooth transceiver to the PC, where the post-collection calculations take place and the final results are shown to the user through the graphical user interface. Taking a closer look into our device, this is a hardware layout of our vibrometer. As you can see, the MMA 7361 is the triaxial accelerometer that we were using, and each axis of the accelerometer is fed through a low-pass filter before being interfaced into the big microcontroller. Also, the microphone is fed into an amplifier circuit before being interfaced to the microcontroller as well. We had some timing issues with operating the accelerometer and the microphone at the same time, so we had to test the microphone separately in the end. The RN41 is our Bluetooth transceiver. It has all the pins necessary for handshake with the PC, as well as data transfer at about 9600 bits per second, and it's transmitting serially. This is just a software flowchart of our embedded controller software, everything from initialization of the ports to the modules that we use, including the ADC and the UART, the logic behind sampling and conversion of each analog channels. So 3 channels for the accelerometer and 1 for the microphone. After each sampling and conversion, the value is stored in a buffer before being sent to the Bluetooth module for transmitting to the PC. And that occurs approximately every 200 milliseconds, so every second you have about 5 samples going to the PC. And at interrupt, the X, Y, and Z are sent to the PC for further processing.
Displays are a post-data collection process. We have the microcontroller take an input from the accelerometer and runs it through the ADC and outputs an ADC value. With that ADC value, we can calculate the acceleration that the microcontroller is detecting using that split equation. And from the equation, we can see that at 512 ADC value, the accelerometer is detecting 0 meters per second squared. So it's not moving. And when we have the acceleration, we calculate the power for X, Y, and Z axes. And once we have the power, we calculate the power in dB, so we can graph the power of each axis in dB. And since we also want to graph with the overall view of the product, see how good an engine is or not. do the vector addition, which is the square root of the axis squared, sum it up. And this is a video for our vibrometer being tested. We're testing it on a 2-liter inline-4 Volkswagen Jetta engine. And we're going to see our vibrometer here on top of the engine. And once we give it power, you're going to see the power LED turn on. The Bluetooth module, which is the red device here, is going to turn on a red light, which means it's on, but it's not transmitting. When the green light turns on, it's going to start transmitting the data. And here are the ADC values. And turn the car on, and you see that the values start changing. This is the X, Y, and Z column. And we're just going to test it for a few more seconds. And as we can see, that's our laptop. And this is spit capture off our laptop that's receiving the values from the Bluetooth module. We're going to rev the engine to about 3,000 RPM. We're going to take some data points at 3,000 RPM. And you see here, the engine being better. After we rev the engine for a few seconds, we're going to bring it back to idle, turn our device off, stop the data collection. We're going to save the file, and after we save the file, we're going to analyze the file.
With that saved data, our group decided to create a graphical user interface, or a GUI, to analyze the data and create a program easy enough for users who have little or no experience with the program or device itself. Our program is developed in NetBeans IDE, and we use the Java Swing library to implement the design, the buttons, and the functionality of the program itself. The user will have a category and a subcategory to choose which device they're using. And in our case, we're using a car engine. From here, the user will take the files that was saved that we mentioned before, and will import the raw data values, the baseline data values, and also the XYZ components from the accelerometer in our vibrometer. From here, the user will be able to see whether the values are inputted by looking at the text fields available here. And from here, the program will analyze the values and output a graphical display of the results. The first graph shows the baseline values versus the raw data values, and it points out every point throughout the whole testing experiment. The next graph will show a average of the baseline testing and the raw data values, and it will take the average between the two and give a percent difference from that. With that percent difference, you can tell how good or bad the engine is. And from here, when you exit out of the graph, it will show the percent difference on the far right-hand corner, and you can determine with the key that we provided if the engine is good or moderate or in bad condition. From here, the basic users can also, if the user is a little more experienced with these files, he can continue on with professional view, and it shows more in-depth analysis of our XYZ components and our averages of those. They can look at each component individually, or they can look at the average altogether. They can also use the average temperature of the experiment
Now, to validate what our initial assumptions were, which is that the band we would be measuring in is around 3,000 to 4,500 hertz, we went and performed a power spectral density, or PSD plot. We did it for both the idle state and the revving state, 3,000 RPM. As it may be noticeable, kind of lighting here. For the idle state, the frequency bands are a little bit more farther apart, which is what we expected. You're going to be looking at the initial peak due to the engine revving when you started up, and then the power band peaking at around 4,500, as you can see right there. That's mainly due to the engine just idling, coming up and coming down just to keep RPM. Now going to the 3,000 plot, the frequency bands are a little bit more closer together, but the peaks are still around the 3,000, 4,500 range that we wanted. We did go ahead and analyze that on a larger spectrum. The higher frequencies just generated more noise, which we didn't want, so we went ahead and created filters to take care of that. In this particular plot, we went ahead and analyzed 2 additional vehicles on top of the Volkswagen Jetta. show that Vibrometer can go ahead and measure, distinguish between different vehicles, different years to generate what the user wants to see. For the baseline being the green value right here, you can notice that the Jetta, which is the gray plaque, is very close to the baseline, which is what we expect for a car in good condition that's been regularly maintained. With the 99 Civic, the yellow line, the trend is a little bit farther than baseline, which is expected for a 99, and then the older vehicle was generating pretty much far away from the baseline. Being an older vehicle, you kind of expect it to rumble more when you start it up. Now, when we went into revving the engine, the plot's a little counterintuitive. Now, for the same three cars, baseline again being green, the Volkswagen Jetta did go ahead and provide a lower band, or a lower power band. We went ahead and essentially inferred that to the car being able to keep its structure, have good force. With the Civic and the 94 Chevy, they did provide a higher band closer to the baseline due to essentially engine rumble. Older vehicles, when you rev it up, they do shake a lot more. Another comparison we wanted to show is essentially going back to the Jetta. The Z-axis initially measuring the up and down motion of the engine. We wanted to go ahead and just distinguish that under idle state and under rev state, there is an absolute difference. The green line being the rev range, or the rev state, it is essentially much higher than the idle. Again, idle is starting to peak initially due to the engine rev, and then it'll go ahead and slow down just to keep its RPM as it goes in rev magic, versus when we rev the engine up and down, power bands do rise. Now, the cost of our particular prototype was approximately $165, so it was mainly due to purchasing PIC sensors, the microcontroller, as well as the Bluetooth sensor. This is on a per unit scale. When we go ahead and mass produce it, it does go ahead and cheapen up the cost a bit. With the product being approximately $57, it is way under what we predict our cost to be. We expect it to be around $70. It is still very cheap in comparison to non-laser based items being around $500 to laser based items costing around $2,000 to $3,000. So this is definitely an affordable off-the-shelf unit. The particular man hours was distinguished over a year's time, basically from research to actual production, costing at a rate of about $30 per hour per person. The cost was about $38,000 to $39,000 total. We did go ahead and distinguish the efforts by grouping our strengths together. We went ahead and divided up the work into 5 different categories: hardware, software, post-collection calculation and signal processing, and then into the GUI, and then finally the testing. Again, everything was based essentially on each of our strengths. Now, lessons learned, we did go ahead and learn the hard way that unpredicted things were to happen. Essentially, you can never predict, obviously, the unexpected. Even with the time allotted for it, things are still going to arise. Creating these for ultimate plans as we learn in class, essentially plan A to Z is what we really need. There is a necessity to realize the difference between theory and practicality. Sometimes you just need to learn to cut your losses and move on. Essentially for us, it was on the USB. We wasted approximately 2 to 3 weeks time just trying to figure out how to utilize the USB being our main port of communication. So we had to, again, just cut our losses with that and move on to the secondary being Bluetooth. However, with this particular project, hard work and good chemistry is what pulled us through. It got us taken care of. And many thanks to Dr. Packowitz for being our faculty advisor and being able to assist us with any issues that we had, as well as Dr. Lloyd for his feedback and presentation of our documents.